Hello everyone, in this video we will cover the section 6.1. In this section we will see inner product, length and orthogonality of two vectors. We will start the chapter 6. First we will see the definition of inner product. Actually you know the definition of this product for vectors in R³ from calculus 2. If U and V are vectors in Rn, then we regard U and V as n by 1 matrices. You know, in the first chapter, second chapter, third chapter, and so on. In Rn, vectors are denoted by, in matrix notation, like this. N by 1. For example, we represent U, the vector U, and it has components U1. U2 blah blah un, okay, or vector V has the representation in matrix notation in this form, V1 V2 blah blah Vn. Vectors are considered as n by 1 matrices. We have n rows and just one column to represent vectors. And the transpose U is a 1 by n matrix. What is the transpose of this vector? So, you know, we change the rows, we interchange the rows and columns. So just we have one column. So for the transpose of U, just we will have one row. The columns become rows for the transpose. Therefore, we write U1, U2, blah blah, Un. So just we have one row and n columns. And in each column, just we have exactly one entry, as you can see. This is the transpose of the vector U. So the transpose is 1 by n matrix, and the matrix product of the transpose of U and V is a 1 by 1 matrix. Let's see. Let's open a new document first. Okay. So the transpose of U and V, we apply matrix product, matrix multiplication. So we have one row for the transpose of U, U1, U2, blah blah, Un, and the vector V has the representation like this one, V1, V2, blah blah, Vn. So from here, this is 1 by n matrix, and this is n by 1 matrix. So this is equal to, we cancel the common number n, so we will obtain 1 by 1 matrix after the multiplication. And according to the rule, we take the row and we take the column directly for applying multiplication. So we have U1 times V1 plus U2 times V2 plus blah blah Un times Vn. Un times Vn. We have 1 by 1 matrix. Namely, just we have a single entry for the result of the matrix multiplication for the transpose of U and V. So we have 1 by 1 matrix like this one, which we write as a single real number without brackets. Namely, for the result, we don't use the brackets for this product. Directly we write U1 V1 plus U2 V2 blah blah Un Vn. Okay, just we have a single real number. Single real number. Therefore, this number is called, in the matrix multiplication of them, is called the inner product of U and V, and it is written as U dot product V. This inner product is also referred to as a dot product. In other words, dot product or inner product of two vectors denoted by U dot product V is a single real number, which is the matrix multiplication of the transpose of U and the vector V, written by U1 V1 plus U2 V2 plus blah blah UN Vn. And we have another notation for the inner product, so this is called the inner product or dot product of U and V. And another notation is written here, UV, inner product of U and V, or U dot product V. So this is equal to this single real number. Actually, this is the matrix multiplication of the transpose of U and V. We have three representations for inner product or dot product of two vectors. Okay. So this inner product is also referred to as a dot product, as I said, and here you see the calculation that we did. The inner product of U and V is written in this form. Of course, we have properties before the properties. Let's see an example, a simple example to understand very well for the definition. So let's find U dot product V and V dot product U for the vectors. U has the components 2, minus 5, 1, and V has the components 3, 2, minus 3. 3, 2, minus 3. So U dot product V is equal to, because of the definition, we will multiply the corresponding entries U1, V1, namely 2 times 3. 2 times 3 becomes 6, plus minus 5 times 2. So we have minus 10. Plus 1 times minus 3, so we have minus 3, and addition of them will be minus 7. And V times, for the second one, V dot product U. So first we take the entries of V. 3 times 2, we have again 6. 2 times minus 5, we have again minus 10. Plus minus 3 times 1, we have minus 3. So this one is again minus 7. And from this example we see actually, and this can be generalized, U dot product V is actually equal to V dot product U, which means that we have the commutativity property, namely we can change the places of the vectors for the inner product. The order is not important when we apply this operation. The order is not important. We can change the places of them. because we have the same result. Okay, this is one of the properties of the inner product in real vector space. So u, v and w vectors in Rn and Cb a scalar, then as we see, we have the commutativity property. We can change the order of the vectors. The order is not important. And we can distribute the vector into the parentheses when we apply inner product over the addition or subtraction, as you can see. First we can apply addition for the vectors u and v, and then we can apply dot product, or first distributing this vector into the parentheses, we can apply dot products and then we can add the results. And when we have a multiple of a vector for one of them, u or v, so this scalar can be written outside of the dot product, like this one. Okay, namely the place of the number is not important. You can write any place as you want. And of course, always u dot product u is bigger than or equal to 0, because if we apply the definition u dot product u in R cube, for example, in R cube, so we have u has the components u1, u2, u3. So the dot product of u by itself will be, we have the same entry u1, the multiplication of them will be u1 squared plus u2 squared plus u3 squared, and every term here is non-negative, which means that the addition of them is also non-negative. If this is equal to 0, if this one is equal to 0, because of the addition, as you can see, this is the addition of squares of numbers. To get 0, everyone should be 0. Everyone has to be 0. So u1 is equal to 0, u2 and u3. Therefore, all components will be 0, which means that u is the 0 vector. And conversely, if u is a 0 vector, so the dot product by itself will be 0, since every component is 0. Okay. If v is in Rn with entries v1 blah blah v, and then the square root of v times v is defined because v dot product v is non-negative, that we saw here. Okay, so this has a special name, which is said to be length or norm of the vector v. The length of v, or the norm of v, is the non-negative scalar denoted by this one, defined by the norm of the vector v, or the length of the vector v is the square root of dot product of the vector v by itself. As you can see, the dot product will be equal to v1 squared plus v2 squared blah blah vn squared, and we take the square root of this number, and this is called the length of v. And the square of the length of v is actually equal to, this is wrong, the square of v will be just the dot product of v by itself. Okay, suppose v is in R square. Let's say v has two components, a and b. So the length of v is the square root of the dot product by itself, which is equal to square root of v1, or we have the components a and b, therefore we write a squared plus b squared. Let's see now the geometric meaning of this definition. If we identify v with a geometric point in the plane as usual, then v, the length v, coincide with the standard notion of the length of the line segment from the origin to v. Namely, if we consider the vector v in the coordinate system, can be this one, for example, this is the vector v. So, and the components are a and b. This is a, and the second component is b. And the length of the vector v will be actually the distance from the origin to the terminal point. The terminal point of the vector v will be actually this one, the length of v, because we have actually a perpendicular triangle here, and this length, this line segment, is the hypotenuse of this perpendicular triangle. And using the Seguran Theorem, we have the length of the horizontal distance, and the vertical distance is b, and the line segment from the origin to the terminal point is equal to the length of the vector v, the norm of the vector v, as you can see. For any scalar c, the length c times v is the absolute value of c times the length of v. Okay, we can prove easily this one. Let's prove. Namely, we want to find the equality. The norm of c times v is equal to the length of c, the absolute value of the number c times the length of vector v. Okay, let's prove this equality in R cube. Namely, we have three components: a, v1, v2, v3. v1, v2, v3 in R cube. So from here we calculate c times v. So c times v becomes c times v1, c times v2, c times v3. And from here the length, the norm of this vector, is equal to, from the definition directly we can write square root of c squared v1 squared plus the square of c times v2 squared plus c squared plus, times v3 squared. And in every term we have c squared, which means that we can take a parenthesis of c squared. Therefore it is equal to square root of c squared times v1 squared plus v2 squared plus v3 squared, and this is equal to, we don't know c is negative or positive. Therefore when we write c squared outside of the square root, we use the absolute value. Okay, therefore for any real number, we don't know it is positive or negative. Generally the square root of c squared is equal to absolute value of c. Therefore, it cannot be negative because the square root cannot be negative. Therefore, we take the absolute value of the number c. So we write the absolute value of c times square root of v1 squared plus v2 squared plus v3 squared, which means that c times the absolute value of c times the norm of the vector v. Okay, this is the proof of this equality. Directly it follows from the definition. And a vector whose length is equal to 1 is called a unit vector. Okay, called a unit vector. Let's do an example about that also. If the norm of the vector v is equal to 1, so we say v is a unit vector. Unit vector. For example, v has the components 1, minus 2, 2, 0. Find a unit vector in the direction of the vector v. Okay, we have a vector v geometrically. For example, what is the components? What are the components of a unit vector in the direction of v? We have the same direction, and let's say for the unit vector which is in the same direction of v, u. Okay, u is a unit vector in the direction of v. In the direction of v. This is the vector u and this one is v. So first we need to calculate the norm of v, which is equal to square root of 1 plus 4 plus 4 plus 0. We take the squares of the entries and we add them, and we take the square root of this addition, and we obtain the norm, which is equal to 9, square root of 9, which is equal to 3. The norm of the vector v. And to find a unit vector in the direction of v, u will be in the form 1 over the norm of the vector v, times v. So we have 1 over 3, and the components are 1, minus 2, 2, 0, which is equal to 1 over 3 minus 2 over 3, 2 over 3, 0. Okay, so this one is a unit vector in the direction of v, because you see this vector is a multiple of v, which means that we have in the same direction. This one is a multiple of v. And to check that it is a unit vector or not, it is enough to find its length, namely the norm. So this is equal to, from the definition, 1 over 9 plus 4 over 9 plus 4 over 9 plus 0. So from here we obtain 9 over 9 becomes 1, so it is equal to 1, which means that it is a unit vector in the direction of v. Therefore, to find a unit vector in the direction of some vector, we will use this formula, 1 over the norm times the vector itself. Okay, and you see the formula here, this one. So the process of creating u from v, namely unit vector in the direction of v, unit vector in the direction of v, is sometimes called normalizing v, and we say that u is in the same direction as v, as we can talk about, and you see the example here. We solve this one. And another important definition for u and v in Rn, the distance between u and v, namely we define distance between two vectors, written as dist uv, is the length of the vector u minus v. In other words, distance between u and v is the norm of the vector u minus v. Okay, norm of the vector u minus v. Compute the distance between the vectors 7, 1 and 3, 2. First we take the subtraction of them. The components become 4 minus 1, and the length will be the square root of 4 squared plus minus 1 squared, which is square root of 17. Okay, 17. Another example. In R cube, u has the components 7, 1, minus 1. V has the components 3, 2, minus 2. So the distance between them is equal to the length of the vector u minus v, which is equal to square root of, what is u minus v? So the components are 4 minus 1 plus 1. U minus v, minus minus 2 becomes plus 2, minus 1 becomes 1. So 16, 1 plus 1, the squares, the square of the components. So we have square root of 18, or 3 times square root of 2. Okay. And geometrically we understand that if we consider the vectors u and v in this example in the two-dimensional coordinate system, you see v has the components 3, 2. So this is the vector v. 3 x-axis and y-axis, second component is 2. And u is U has the component 7, 1. This is the terminal point. Therefore, from the origin to terminal point, we create the shape of the vector U. This is the vector V, and this is the vector U. To find U minus V, we use the parallelogram rule. Parallelogram rule. This one is good. Parallelogram rule. Namely, we move the negative V to here to find U minus V, because we want to apply addition for U and minus V, actually, by writing U plus minus V. For this, we use the parallelogram rule. So minus V becomes in this form. Minus V we have in the opposite direction. Therefore, we unite the terminal point of the vector U and the initial point of V. Therefore, we have this one by using the parallelogram rule. And by combining the origin and the terminal point of this combination, we find U minus V, which is blue one, as you can see. This is U minus V. U minus V. Or by moving this vector to here, this is also U minus V. And our aim is to find the length of this one, to find the distance between U and V. Okay, actually the distance between U and V is the distance between the terminal point geometrically, as you can see. Okay, because the length of this line segment, or the norm of this vector, which is U minus V, is the distance between the terminal point of V and the terminal point of U, which is very important. Notice that the parallelogram in the above figure shows that the distance from U to V is the same as the distance from U minus V to 0. Okay. And now we will see the orthogonality of two vectors. Two vectors U and V in Rn are orthogonal to each other if the dot product of them is equal to 0. The dot product of them is equal to 0. The 0 vector is orthogonal to every vector in Rn, because when we apply dot product for 0 vector and any vector, we will obtain always 0, because every component of the 0 vector is equal to number 0, which means that dot product will be 0. And two vectors U and V are orthogonal if and only if the square of the norm of U plus V is equal to the square of the norm of U plus the square of V. The square of V, which is called the Seguran Theorem, actually. Theorem. This is the real definition of the Seguran Theorem. Let's prove this theorem. Seguran Theorem. U, the square of the norm of u plus v is equal to the square of the norm of u plus the square of the norm of v. Actually, we have a perpendicular triangle x, y, and z, x, y, and z, and if we consider x is in this direction, this is a vector, and v is another one, and the addition of them will be the vector z, and the angle between x and y is 90 degrees, and we will prove the length, the square of the length of x plus the square of the length of y is equal to the square of the length of z. Actually, z is the addition of x and y, therefore we have x plus y squared. So this is called Seguran Theorem. Okay, so how can we prove this theorem? So first we will start from the left side of this equality. So u plus v squared is equal to actually we know the length of some vector is equal to square root of dot product of the vector by itself. Okay, and we take the square, therefore it becomes just the dot product of v by itself. We remove the square root since we take the square. So we write u plus v dot product u plus v. And we have the distribution property. So if we consider this one just a vector, as a vector, so it is equal to, namely, u plus v squared is equal to u plus v dot product u plus v dot product v. Okay, we distribute the first one into the parentheses, and from here we obtain, by using the same property, we distribute this one into the parentheses and this one. So we have u dot product u plus v dot product u plus u dot product v plus v dot product v. And from here we know this theorem is valid if two vectors are orthogonal, namely the angle between them is 90 degrees. Okay, this is valid if u and v are orthogonal to each other, which means that the dot product of them will be equal to 0. From the definition, u dot product v is equal to 0. U dot product v is equal to 0 from the definition written here. Therefore, we understand that this one is equal to 0, This one is also equal to 0. Therefore, just we have u dot product u means that the square of the length of u plus, similarly, the last one will be the square of length of v. That's it. We have the equality. We have the equality. And conversely, we have two sides for this theorem. Conversely, if we have just this equality, we don't know yet they are orthogonal to each other or not. Just we know this equation, this one. We don't know yet they are orthogonal, but if we have this equality for two vectors, which are u and v, also we can say they are orthogonal. This is equivalent to the definition of the orthogonality of two vectors, because normally let's like the previous calculation, the left side of this equation will be u dot product u plus v dot product u plus u dot product v, and the order is not important. They state the same things. Therefore, we write 2 times u dot product v plus the last one v dot product v. V dot product v is equal to the right side. Actually, this one is equal to u dot product u from the definition, and the second one is similarly v dot product v. Removing them, we have the same things in both sides. So on the left hand side, just we have 2 times u dot product v, and on the right hand side we have 0, which means that u dot product v is equal to 0, which means that u and v are orthogonal. Okay, just when we have this equality, we understand this is orthogonal. If conversely, if u and v are orthogonal, so we obtain this one. Okay, we have two side proofs here. And lastly, let's do an example about that. A has the components -2, 1. B has the components -3, 1. Let's say 6. Let's say 6. So prove that, verify the equality u plus v squared is equal to the square of the length of u plus the square of the length of v. The square of the length of v. If we have this equality, so we understand that they are orthogonal to each other. So first we calculate a plus b, which is equal to minus 5 plus 7, and the length of this one is equal to 25, 49 is equal to 14, 74, and the length of first one is equal to 4 plus 1, which is equal to 5, square root of 5, and the square of this one is equal to 5. And for the second one, the length is equal to, from the definition, 9 plus 9 plus 36, 9 plus 36, so we have 45, and the square of this one becomes 45, and the left hand side, namely this one, is equal to 74, and the right hand side is equal to 5 plus 45, so they are not equal to each other, which means that they are not orthogonal. Let's check by using the main definition, namely to say that they are orthogonal to each other, the dot product of them should be equal to 0. When we look at the dot product, so we have plus 6 becomes 12. Therefore, they are not orthogonal, or from here we understand that they are not orthogonal. If we have minus 1 here, let's calculate again. So the addition becomes, in the case the second component is minus 1, okay, addition of them will be minus 5, minus 5, and the square of the length of addition will be 25 plus 25 will be 50, and we know the squares. The square of the length of A is equal to, so 4 plus 1 becomes 5, and we know B, it is equal to 45, so the addition of them 50, which means that we have this equality. The right hand side is 50, the left hand side is 50, so we understand that they are orthogonal because of this equality, and we can check the dot product of them will be plus 6 plus minus 1 times 6 becomes minus 6, which is equal to 0. And lastly, we will talk about orthogonal complements. If a vector Z is orthogonal to every vector in a subspace W of Rn, then Z is said to be orthogonal to the subspace W. Namely, if Z is orthogonal to every vector in the subspace W, so we say this thing. So we say Z is orthogonal to the subspace. The set of all vectors Z that are orthogonal to the subspace W is called the orthogonal complement. Orthogonal complement of W, and is denoted by this one, the set of all vectors that are orthogonal V is called orthogonal complement. In set notation it is written as, it includes all vectors Z such that Z is orthogonal to W. Okay, we have the one condition, which is that Z is orthogonal to W, and this is the notation for this set, and read as V perpendicular or simply V perp. So a vector X is in this set if and only if X is orthogonal to every vector in a set that spans W, and this special set is a subspace of Rn. And here we have an important theorem. The dot product of U and V is equal to the length of U times the length of V times cosine V, cosine actually theta, where theta is angle between them. Actually, you know this formula from calculus 2. To verify this formula for vectors in R square, consider the triangle shown in the figure. As you can see, U and V, the length of U, the length of V, and the angle between them is special V, okay, special theta actually, and we want to calculate the dot product of them by using this angle. So by the law of cosines, we know the line segment opposite to angle is U minus V, okay? Like the previous shape, you can calculate easily. This line segment is corresponding to the vector U minus V. This is the vector U. This one is V. We calculated how we can find U minus V from the previous examples here. And now directly we use the law of cosines. If you remember, the square of this distance is equal to the square root of this one and the square root of this one minus 2 times the length of U, the length of V, times cosine of this angle between two vectors, which can be rearranged to produce the equations. And by writing this one on the left hand side and this one on the right hand side, so we have U times the length of U times the length of V times cosine special V is equal to 1 over 2 obtained from this scalar U squared plus V squared, these ones and this one, U minus V squared, and using the definition of the norm you can find them, okay. And after calculating this term, we obtain 2 times U1 V1 plus 2 times U2 V2, and at the beginning we have 1 over 2, and by removing 2's, by simplifying them, we obtain U1 V1 plus U2 V2, which means that we have the dot product of vectors U and V. The verification for R cube is similar. You can use the similar proof. And when n is bigger than 3, namely for higher dimensions, the formula may be used to define the angle between two vectors. So this formula is used to define the angle between two vectors in higher dimensions of the real vector spaces. And in statistics, the value of cosine special V defined by this formula for suitable vectors u and v is called a correlation coefficient. Okay, therefore this is very important formula, and you know actually from calculus 2. Thank you very much.